All right. So in this video, I'm actually going to show you how to find the inverse of a function. In that first video, the key concept was that if you combine two inverse functions, that they basically cancel each other out. Like if you do function composition, one with the other, they undo each other. All right. Here's how you're going to find the inverse of a function. So it started with f of x, but I'm going to just replace that f of x with a y. They're pretty much interchangeable is what they are. Uh, to find the inverse, you're going to swap the x and the y here. All right, you're going to just swap these guys out. Oh, I should say to find the inverse of a function, there should be like a little caveat right here. If it exists, all right, the inverse of a function may not exist. All right, we'll talk about that later. You're going to swap the x and the y. So it's going to be x equals 3y minus 1. And then you're going to solve for y. All right, now I'm just going to resolve this equation for y. Add 1 to both sides, plus 1, plus 1. You get x plus 1 is equal to 3y, and then you divide by 3. Divide by 3. And so this is what I get. I get y equals x plus 1, all of that stuff, divided by 3. So this is the inverse of that. And it's really not too bad when you're dealing with linear functions. Like we'll do some more examples in the next video. But linear functions are pretty straightforward. There's nothing crazy that you have to watch out for. But that's how you do it. You swap the x and the y, and then you solve that equation. Like I solved this equation for the y. Okay. And if you wanted to check your answer, I guess you could, actually plug in a number for x. Like, let's say I plugged in the number 6 for x. 3 times 6 is 18. 18 minus 1, I get 17. What that means is that if these are truly inverses of each other, then whenever I come down to this function, if I plug in 17 for x, I should get a 6 back. All right, 17 plus 1 is 18, and then 18 divided by 3 is 6. All right, that's what should happen. These x's and y's should just be swapped. All right, that's the idea. That's the idea. All right, next one here. I'm not going to do that example that I had from before. Here, I'll keep it upright. Let's say I had y equals square root of x minus 3 plus 1. So when you're dealing with square roots, this is going to involve a little bit of extra thinking, but it's not too bad, not too bad. So start off the same way, swap these x's and y's. X will equal the square root of y minus 3 plus 1, and then we have to solve for y. So I need to get the square root thing by itself first. Minus 1, minus 1. I get x minus 1, y minus 3. Then I need to square both sides. So when you square that, those are just going to cancel out. That'll leave you with a y minus 3. Now, when we square this, remember you got to take that whole thing and raise it to the second power. If we were simplifying it, I would do x minus 1 times itself. But I'm actually going to leave my answer. I'm going to leave it like this, x minus 1 squared. And then lastly is you'll add 3 to both sides. Add 3 to both sides. Now when I add 3 to the left side here, it's not going to go in the parentheses because you have that x minus 1 squared thing. That squared is kind of keeping this on lockdown. So what your answer is going to be is y equals x minus 1 all squared plus 3. So these two are inverses of each other with a little star here because there is a disclaimer. But notice I'm taking x, I'm subtracting it by 3, and I'm square rooting, and then I'm adding 1. So down here, the complete opposite is happening. I'm minusing 1 instead of adding 1. I'm squaring it instead of square rooting, and I'm adding 3. Okay? Let me go over the graphs here. Look at what the graphs look like. There's another concept with the graphs. All right, so these two are the inverses of each other. And you may not be able to tell, there's not a whole lot going on with the picture here. See they cross, that's about it. But the fact that we swapped that x and y is going to do some, it's going to have some nice properties. So this is the graph of y equals x. And now you can definitely see something going on with the graphs, I hope. They are a reflection of each other across this dashed line, the y equals x line. So if I look at, let's say I find a point that's on this blue one, 2, what is it, 2 comma 5? Yeah, 2 comma 5, I believe. Yeah, that one should be on there. So if I'm going to graph 2 comma 5, what that means is that on my green line, on the inverse, I should find 5 comma 2. All right, I should find the reverse of it. And there it is right there, 5 comma 2. 5 comma 2. And these points are a reflection of each other across the line y equals x. And that's going to be true for every single point on this line. So if I look at 8 comma 3 and 3 comma 8, all right, they are a reflection of each other across that line y equals x. So that's key concept number 2, is that inverses, they are a reflection of each other across the line y equals x. You need to remember that. All right, that's something that's always true about inverses. Get rid of some of this stuff here. All right, now if I take a look here, there's my original square root graph, and here's my my inverse. And you can tell it's almost a reflection. Like what I'm missing here is, like, I'm missing the second half maybe of this purple one, but actually the purple one's the original. My problem actually lies with my inverse. What you have to do here is you kind of have to ignore half of the picture. So where the vertex is here, that's going to be my cutoff point. I'm actually going to restrict the domain, or I'm going to ignore half of this graph, and I'll try to illustrate why here. So you know how we swapped the x and the y? What that was doing, what that kind of does, is it swaps the domain and the range. And you get these two facts, and these are something that's always true about, it's another thing it's another concept, another thing that's always true with inverse functions, is that the domain of one is the range of the other. So the domain of my original function will be the range of my inverse, right? And the range of my original function will be the domain of my inverse, right? And that's going to be the thing that's going on with this graph here. See, the range of my original function, the range of my original, which is this purple one here, is from 1 to infinity. Remember, the range is the y values. So from 1 to infinity is the range. That needs to be the domain of my inverse function over here. So 1 to infinity. What I need to do on this right here, since this guy has a range from 1 to infinity, or all the values that are greater than or equal to 1, this one needs to have that as a domain. So I need to restrict the domain so that it is only the numbers from 1 to infinity. And graphically what that does is it just cuts this, it's cutting this graph in half. So like on Desmos, here's how I do it. I take my curly braces, and I'm going to do x is greater than or equal to 1. And now you can see I've only got half of this picture, only from 1 to infinity. That's my domain of my inverse, and that happens to be the range of my original. And now you can see that they truly are a reflection of each other across that line. So anytime that you're dealing with the square root functions, you're going to have to kind of go through this little process. You need to recognize it's easy to, I mean, the algebra behind it, actually finding the inverse, that's not that big of a deal. But it's this last part, the part where you have to restrict the domain. The way it works is the range of your original function here, so it was from 1 to infinity, that has to be the domain of your inverse. So the domain of this one starts at 1 and it goes to the right forever. All right, that's the key concept number 3. All right, we'll do some more examples here in a sec.